Hi, I'm Stuart Jensen, a physics professor at Alma College, and I'm eager to share with a broad general audience some cool ideas in physics research that I've been studying recently, partly with a student, Jack Poling, about a new way to teach and think about some fundamental topics in physics using a mathematical tool called a bivectors that most physicists and mathematicians haven't ever actually run into before. So, to be able to tell you about this, I have to start by telling you that I'm going to have to give you some background that's challenging for students. And what I want you to get from this is that it's challenging because I'm going to make it better in the end. So what do I mean by challenging for students? This is the concept. The concept we're looking at here is the concept of right-hand rules and cross products. These come up in various places in physics, and there's a study, Deprez et al. Did this study of students where they had just taught them a course on electromagnetism, and they had just learned about right-hand rules and cross products. And then they gave them this a series of 3 7-question quizzes on how they could solve problems using cross products. And from these graphs, you may be able to see that in none of the 3 contexts, whether different physics contexts or pure math, in none of the contexts did most students get even half of the questions right. This was, 3 out of 7 or 1 out of 7 are often the most common number of questions right along the way. That's the level at which these things are challenging and at which students struggle with these concepts. Soon, you will get to struggle for yourself. Our eventual goal in our research is to replace these awkward methods with a new language that's both more intuitive and more fundamental. But we'll get there. First, I have to show you where these concepts fit in the story of physics. And I guess, essentially, I'm going to carry on this talk from the darkness to the light. I'm going to start by explaining how we describe different physical quantities in physics, what types of mathematical descriptions and objects we use to describe things. Then I'll talk about, beyond just the student learning difficulties I just talked about, I'll talk about some specifics about ways that right-hand rules and cross products are challenging for people. And then finally I'll tell you about this bivector story and why we think it's a better way of doing these things. All right, so starting with how do we describe things in physics. Physics is all about observing the world and assigning mathematical descriptions to it, and a lot of things we see are just, all we care about is how much of it there is, how much is there. So mass, for example, is just a single number. How much mass is in those dumbbells? How much temperature? What's the temperature today? What's that single number? How much electric charge is on that balloon you just rubbed on your head? What time is it? All of these are things that's just a number with some units, not a direction. It only cares about an amount of stuff. Those are called scalar quantities if they only care about the amount. On the other hand, there are things called vector quantities, where we care about not just an amount, but also a direction in space. So for example, if we have some origin in space, like the intersection of First and Main downtown or something, you can talk about where something is located by saying, yeah, that's 2 miles northeast of here, or it's 1 block east and 3 blocks south, or something like that. You can talk about those different positions by giving not just a distance, but also a direction. Mathematically, we can visualize that as an arrow. An arrow has a length, a magnitude, and a direction, a way it points in space. And so quantities represented this way are called vector quantities. Position is one, velocity is another. An object's velocity is not just how fast it's going, represented by the length of the arrow, but which direction it's moving. I have this picture here of a baseball, arcing through the air, and you can see in this picture that the velocity vector arrows show that as the baseball arcs through the air, it changes its direction and its speed. Both its magnitude and direction of the arrow change as it moves. That's because velocity cares about both those things. Force is another thing where you care about not just how hard you push, but which way you're pushing something. Or, in a more abstract example, the electric field created by positive and negative charges is also represented by a little vector arrow. All of these are vector quantities. So here's another quantity to consider. What about rotating systems? I've got 3 of them that I've illustrated here. One of them is a clock on the wall moving moving clockwise in the wall, clockwise of course. One of them is a merry-go-round sitting on the ground that's just rotating around on the ground. And one is a little harder to visualize. I guess I could have done a video of myself or something. It's a mass on a string. that is just the ball is a ball on the end of a string that's just rotating around in circles in the air. And I want to say, what kind of quantity do you think we could use to describe these? Think about it for a minute. Clearly, we care about how fast they're rotating. Faster or slower matters, so the magnitude of the quantity matters. But there's also something here about their orientation in space. Something that is rotating on the wall is different than something that's rotating on the ground. Those are different somehow. So the traditional description of these things uses vectors. We talk about the angular velocity of that second hand of the clock as it rotates. And that angular velocity is something that represents that direction of rotation. Well, how do you represent something going in circles by a single vector? We use what's called a right-hand rule. We use the axis of rotation of that second hand as the orientation in space. So the axis of rotation in the second hand is the little axle, the screw or whatever that's holding it onto the wall, into and out of the screen here. And then how do we decide whether it's in or out? Well, this is where we use a right-hand rule. You take your fingers of your right hand, not your left hand, sorry left-handed people, we're discriminating. You take the fingers of your left hand and you point the tips of your fingers following that second hand around the clock as it goes. And as you follow around, you then stick out your thumb and it points into the wall, into the screen here. Your thumb points into the screen. That's the right-hand rule telling you that the angular velocity vector, in the traditional form, points into the screen. You try it. Here's this merry-go-round going around and around flat in space. Take your right hand and try doing the right-hand rule to figure out the direction of the angular velocity vector of that merry-go-round. I'll give you a second. All right, well, when I do that, I take fingers of my right hand, they go curl around with the merry-go-round, and so my thumb winds up pointing up away from the ground. And sure enough, that's the correct description of this rotating angular velocity. What about the ball on the string? This is this one where the ball is coming around like this. So what do? Try it out. You take your right hand, you curl your fingers around the way the ball is moving, up in front, into the screen on the top, down and back, and my thumb points perpendicular to the circle and the perpendicular to the plane of motion and off in that direction. So what you're probably getting from this is the essential idea that it really matters exactly what direction you hold your hand. Maybe that went okay for you. Maybe, especially if you've seen it before. So good. That's the easy right-hand rule. Let's keep going. For that last example, that ball spinning around on a string, there's another way we can talk about its rotational motion, talking about its angular momentum. And for a point-like object moving past the origin of your measurement, we can use a different way of talking about a right-hand rule, a different type of right-hand rule called a cross-product right-hand rule. What we're going to do here is we're going to multiply two vectors. There's the vector r, the position vector, that goes from, it's sort of like the radius of a circle, that goes from the center of the circle up to where the ball is. And then there's the vector v, the velocity vector of the ball at that moment. This is just one moment in the ball's motion. And at that moment, the ball's velocity looks like it's going sort of into the screen and at a bit of an angle like that. So those are our two vectors. And I want to know what is the direction of angular velocity or angular momentum from that. So I use my right-hand rule here. This is a different right-hand rule. I take my pointer finger and point it along the r direction. I do that. And then I rotate my wrist so that when I stick out my middle finger, it points in the v direction. Guess that's kind of like this. R and then V, kind of like that. And now when I stick out my thumb of my right hand, has to be a right hand, when I stick out my thumb, it goes this way. That's the same direction we got earlier with the other right-hand rule, but this time we use this cross-product three-finger thing. All right, that's another right-hand rule that we can use for rotations. But it's not just rotations that are described by this right-hand rule sort of stuff, cross-product sort of stuff. Magnetic fields, for example. The traditional description of a magnetic field, if you have a bar magnet, up at the top left there, I've got a couple of bar magnets that have their north poles marked with red tape around the end of the magnet. And this illustration shows the magnetic field vector pointing in different directions around these magnets. The traditional description says the magnetic field points out, emerges from north poles, and the magnetic field goes in to south poles of bar magnets like this. You can see that in that picture. Now, if we had a flowing electrical current, you've heard of electromagnets before. If I had a flowing electrical current, I can use a right-hand rule to figure out what magnetic field they produce inside that loop of flowing current. This also works for the bar magnets, but it's a much more subtle argument. So what happens? The current in this picture is going around this way. So I take my right-hand fingers and curl them around along with the flow of the electric charges, the electric current, and my thumb points up, and that's the direction of the magnetic field, up through the middle of that loop. The magnetic field comes up and out through that loop. So magnetic fields, production by currents, given by a right-hand rule. It's great. Almost done this part. One more bit. Charged particles in magnetic field also feel forces due to those magnetic fields. So this is a situation, a scenario where I've got a magnetic field pointing out from the page. Magnetic fields pointing out of the page, and we have a velocity, a velocity vector pointing upward and up the page. And if I want to know what magnetic force that velocity vector will feel, it's a cross product, velocity vector cross product with magnetic field. I don't know why we use B for magnetic field, it's the tradition. So velocity vector is my pointer finger. Then my middle finger, I rotate my wrist until it points out of the page, out of the screen. And my thumb now points in the direction of the force, the magnetic force that particle will feel. And you can see that's going to make that particle go in circles around the magnetic field, if you think about it for a while. The force direction will change as the velocity changes, and it will always make the particle go in circles around that field. So the force vector is perpendicular to velocity and perpendicular to the magnetic field. All right, you've done all these magnetic fields and rotation things, all these right-hand rules. After all those right-hand rules, I know what you're thinking. Yeah, they're hard. This is kind of hard to wrap your head around. It's challenging. Maybe if you've studied cross products before, maybe you're already good at this. But the vast majority of new learners aren't good at it, as I already showed you some data to support. And that's where I want to give you even more detail on some of the downsides of these cross products and right-hand rules. So in particular, we've already seen the data on students getting things wrong. Maybe now you have a much better sense of why so many students got less than half the questions right in these things, because even after learning, that was hard to get used to. Expert physicists get used to it, but beginners take a long time to get there. There's another study that I'm illustrating here on the right-hand side of the page by Kustoch, who studied how reliably students got questions about right-hand rules, magnetism or whatever, correct, depending on how you have to hold your hand for that particular story in the problem. She took vectors A and B, A cross B, and said, how easily can students find the cross product of A and B? And that three finger thing. For some orientations of your hand, like here and here, and your thumb going this way, it's easy to hold your hand that way, or here and here, or here and here. Those are easy orientations to do. Those are the ones shaded in green in this picture. On the other hand, some orientations of the vectors A and B are really awkward to do. A cross B or A cross B. These really awkward ones are shaded in blue, and she found that students are noticeably less successful in answering questions about cross products and right-hand rules when they have to twist their wrist in a funny way. And I don't know about you, but I find it kind of disturbing that we're defining some fundamental principle of the natural world in a way how hard it is to answer the question depends on how flexible your wrists are. That seems like a strange sort of definition to use. Another weird thing about right-hand rules that goes deeper than just student learning is this idea of cross products. This can actually be kind of challenging in situations if you look at the universe in a mirror. So on the left-hand side here, I've illustrated a cross product, R cross V, just one of these angular momentum calculations, where I've got the R vector pointing out of the screen and the V vector pointing up at an angle, and then R cross V points up and to the left there as you see it. And so that's our R cross V. If you do this whole thing in a mirror, you'll find that if you reflect across that vertical plane, you'll find that the r vector points kind of the same way. The v vector now points a different way, and my thumb, my cross product direction, points down. But the mirror image of the original cross product would point up, just up in the other direction, from here to here. That's different than having to flip it and point down that way. It's instead of here, it's here. That fact that the cross product of two vectors has to get flipped when you look at it in a mirror means that it's kind of not exactly a true vector at all. This is often called a pseudo-vector or axial vector quantity. And this idea of pseudo-vector quantity. Stick with that. A pseudo-vector quantity is one that has this weird property that in a mirror it goes wrong. This can throw off even experienced people if they don't think about it carefully. Other things to worry about? In magnetic field stories, we had to use this right-hand rule. It turns out that when you're teaching physics especially, a lot of times for students, three-dimensional thinking is hard. It's nice to be able to just draw an example, have something that fits on a sheet of paper that isn't three-dimensional to do things. Even though physics is three-dimensional, you can simplify things by putting it on a flat sheet of paper. Magnetism doesn't work that way because, as we saw, you need to have a magnetic field out of the page to describe an object that's going in circles, with a velocity and a force both in the plane of the page. It's necessarily three-dimensional thinking. That's hard for people. You can't write down a purely two-dimensional example. For that matter, since the right-hand rule has three fingers, three dimensions to it, there's no way to talk about what would this be if I wanted to talk about relativity, where we're in four-dimensional space-time. Or I'm a string theorist by training. I like to think about universes with 9 or 10 dimensions of space in them. And in those cases, how do I do a right-hand rule in 9 dimensions? The answer is you don't. It's not well defined. So you can't even talk about magnetism in other dimensions, with the right-hand rule. And the two-dimensional cases, you're still stuck with a vector out of the page. It's always three-dimensional. Another problem that students run into with this is that electric fields and magnetic fields get drawn in basically the same way. On the left side of the screen, you'll see that picture of electric fields pointing away from positive charges and toward negative charges. And there are those little vectors there. And the magnetic field of a bar magnet with a north pole and a south pole looks almost the same. Though the students confuse them back and forth all the time. It's very common. And even though they look the same, it turns out their effects are remarkably different. For an electric field, if I had some positive charge, maybe going into the screen or something, it would pass through that electric field region and feel a force in the same direction as the field arrow is pointing. It's a very natural thing to come up with. For the magnetic field, a positive charge moving into the page, into the screen, with the magnetic field shown there at the position I've drawn, its force we saw before. The magnetic force is perpendicular to the magnetic field direction and to the velocity. So these are completely different ways these two different types of fields act, even though they're drawn the same way. And that's a problem for students. All these things, there's research on this, lots of research. Students struggle with these representations where the vector that you draw is perpendicular to the behavior that it's describing. So in rotations, Mashoud and Singh found that even after repeated emphasis in class, students repeatedly revert to the notion that angular velocity, rotational velocity, must somehow lie in the plane of motion. So for a merry-go-round, instead of the correct up out of the plane right-hand rule answer, the students will say, oh, it must be this way or this way or this way or something in the plane. Similarly, that confusion about the directions of magnetic and electric forces and how those are so different, magnetic forces are not are perpendicular to the magnetic field. It's complicated for students. And Guisasola and others and collaborators found that about half of students, even after instruction, came away with the idea that magnets must have electrical charges because it's drawn the same way as electrical charges were, that electric and magnetic fields are mistaken for each other back and forth all the time, and they come away with this idea that magnetic interactions are explained by some central force, that the force on a charged particle would go away from a north pole instead of perpendicular to away. It's complicated. Students struggle with this. So all of this is hard. All right, where do I go with this? How do we make things better? This is where my claim is that we can address all of these challenges by replacing every right-hand rule and cross product in physics with instead a concept called bivectors. What's a bivector? Let's return to our example of rotating systems. We've got our clock going clockwise on the wall. We've got our merry-go-round. We've got our mass on a string. How do these work? How do we describe these in a different way? Instead of trying to describe these things with a little arrow, a vector arrow, what if instead of an imaginary arrow representing the motion, we represented it as an imaginary tile in space? Replace those arrows with tiles. The tile is oriented in the plane of rotation of the object. So the tile for the clock on the wall is a tile parallel to the wall. The tile for the rotating merry-go-round is a tile parallel to the ground. The tile for this rotating mass on a string, ball on a string, is a tile that's in the plane of motion of the ball on the string. Each tile is decorated, is labeled with a little clockwise or counterclockwise arrow showing which form of rotation within that plane, which orientation of rotation in that plane is indicated for that particular object. So these tiles, I don't need to do any right-hand rules for this. You just draw the rotation on the tile. It's directly there. Or this one's fun. For that mass spinning on the string, you remember the cross product thing where we did the r and the v vectors? For this, if you draw the r vector and then you draw the v vector along with it, you start with the r vector and then at the tip of the r vector you start the tail of the v vector. So you draw those two vectors. Those would start out being two sides of a rectangle, or more generally a parallelogram. If you then close off that parallelogram and draw those vectors r and then v around that parallelogram, you have just drawn a tile in the plane of the motion, and the direction around that tile is the direct, r and then v going around the edge of the tile is exactly the direction that the ball is orbiting around its central point. It's all very intuitive. It's straightforward. You draw pictures that make sense to you. Now, you still have to talk to people who've learned the vector way of describing these things, and you can convert to the vector version easily, because it turns out that all you have to do is just say, oh, I'll take my right hand. If you want to use a right hand rule to tell the vector version, I'll just take my right hand and curl it around the tile. Curl my fingers with the tile. My thumb will point perpendicular to the tile in the standard right hand rule direction. I curl my fingers with the tile for the merry-go-round, and my thumb points perpendicular to the tile in the standard right-hand rule direction. So you can still get back to the traditional vector description from this, but by doing the tile first, you're doing something that is concrete, visually represents the motion, rather than this more abstract talk about the axis of rotation business. I like it a lot. Ultimately, I would say that pseudo-vector description, the right-hand rule description, originates from these bivector tiles. We represent these bivectors. Why is a bivector? It's a bivector because we constructed these tiles from two vectors, the r and then the v. Each tile can be thought of as two vectors put together. And the right-hand rule you have to use for this conversion is always the easy one, never the three-finger business, but always just curl your fingers around some arrow. This is not bad. This is a nice way of doing these things. What else does this get us? It turns out that if you do the bivector tile from vectors r and v instead of a cross product from vectors r and v for that example we showed earlier, and you reflect it in a mirror, the bivector orientation flips in a mirror too. What looked counterclockwise at first now looks clockwise because the mirror flipped that too. There's no weird also do the reflection and then reverse it thing. It just reverses on its own in the mirror. So this is the more natural way of describing rotations because you don't have this extra weirdness of the mirrors messing it up. There's magnetic fields that we can describe with bivectors. It turns out that if you have a magnetic field going in, or an electric current going in loops, generating an electromagnetic field, a magnetic field from that electric current, it turns out that the direction, the bivector tile representing the direction of the field in the middle of the loop, is just a little tile with the orientation matching the way the current is going around the loop. It's as easy as that. And they spread out and go out from the loop up above and into it from below, but it still spreads out from there. What that ends up meaning is that from this perspective, a north pole of a magnet is one where the bivector tiles look counterclockwise when you look in, and the south pole of a magnet is one where the bivector tiles look clockwise when you look into the south pole. So that's these definitions. The magnetic field looks this way, and this has benefits. If I want to tell my students a simple two-dimensional magnetic force problem that can fit right on a page of paper, all I have to tell them is that I've got a magnetic field that's represented by a tile counterclockwise in the page of the paper. And if I have a velocity vector going up, the rule they have to learn, there's no weird right-hand rule thing. The rule they learn is if the tile is counterclockwise, then you just need to turn your velocity vector turn your velocity vector clockwise to go with it. 90 degrees opposite the magnetic field tile is what direction the force is. That's not bad. You've already got the picture there. The rule is 90 degrees opposite. You get your force direction right away without some weird right-hand rule business. It's a perfect two-dimensional story. You don't need to have 3D thinking to answer this question. And that's much easier for students. And by the way, all this works in 4 and more dimensions too. The bivector tile story keeps working where in not just 2 or 3 dimensions, it works in higher dimensions as well. It gets more complicated and interesting in fun ways, but that's a different story. Also, it seems plausible that by drawing magnetic fields as bivector tiles instead of as vector arrows, it's going to be much easier for students to distinguish electric from magnetic diagrams. The north and south pole of a magnet with these little tiles coming out of them look very different than a positive and negative charge with arrows coming out. And maybe that will be enough to help students keep the two separate and tell the difference between the two. All right. I hope you're thinking that this is not so bad. This is a thumbs up instead of a thumbs down. The bivector description can give just a direct representation of what you're trying to describe and a direct representation of the sources and forces and things for magnetism. All that comes right there. For those of you who are a bit more mathematically inclined, let me say one slightly technical slide. Anyone who's not mathy, just put your fingers in your ears for a minute. This won't take long. Vectors we usually describe as with 3 components, an x and a y and a z component of a vector that represent how much that vector arrow points along the x or y or z axis, sort of like the projection or the shadow that the arrow casts on that axis. Bivectors can also be represented in components in a very similar way, except bivectors, since they're 2-dimensional tiles instead of 1-dimensional arrows, their projections are onto planes. So the bivector, for example, has a component that is its projection on the xy plane, the shadow it would cast on the xy plane. And the more it's in the xy direction, the bigger that shadow will be, and you'll get an xy component. The yz component is the shadow it casts, the projection onto the yz plane, and so on. And by calling it the xy plane instead of the yx plane, the order of x and y tells you what I'm defining to be positive. An orientation that's in the direction that rotates from x toward y would give a positive value for the xy component. On the other hand, it would give a negative value for the yx component because the yx component is in the direction that goes from y toward x, and x toward y is the opposite. So what this means is that instead of writing a vector as a 3-component vertical sort of column vector, the natural way of writing a bivector is an antisymmetric matrix. Obviously, there's no xx plane, so there's zeros down the diagonal. This is all technicalities for people who don't care about this, and a hint at where this is going. Technically, bivectors are second-rank antisymmetric tensors, contravariant tensors, but that probably means nothing to anyone out there. Very closely related to differential 2 forms. Again, only specialists will know what that means. But the point is there's a mathematical language for this, and if you read my papers on these things, you'll see the mathematical language for bivectors maps just directly one-to-one onto the mathematical language for vectors. You can the LZ component for the vector is the same as the LXY component for the bivector. They exactly map onto each other. The math it's natural in either case, so you can learn it well. Okay, some final technical ideas and things. So some final ideas, big picture ideas. Now that I've talked about the big picture of all the technical of all this, I want to talk about the big picture, where this fits into thinking about physics. First of all, I should comment, I'm not remotely the first person to talk about bivectors. These are things that have come up for years in specialized contexts. I first ran into them when I was studying the classification of space-time manifolds and general relativity. They come up in classification theorems there. I didn't really know what they were doing at the time. That was the only time I'd ever run into them. Most physicists or mathematicians will never run into them. But there is one group of physics people who've talked about bivectors in these contexts of rotations and magnetism quite a bit. And there's this field called geometric algebra that seeks to redefine the mathematics we use for all sorts of physics and mathematical things in very deep and fundamental ways. It's kind of cool. It's a neat structure. Some people are really excited about it. I think it's interesting. I'm not as excited, but I will say, I think it's cooler people studying it, and I've had several of them tell me, I should say, that several of those people in that studying that thing have told me, hey, your work on bivectors, talking about rotations and things using bivectors, is something that geometric algebra people could use to introduce students to this concept of bivectors before they introduce them to how bivectors fit into the larger context of geometric algebra. Basically, geometric algebra is forced to use the bivector description of rotations and of magnetism because that's the more fundamental description, and geometric algebra is really getting at the fundamental pieces of these definitions of things. And so its bivectors naturally come up there, but the problem is that since the geometric algebra people are mostly the only people talking about bivectors these days, it turns out if you look up bivectors on Wikipedia, for example, it's an article about geometric algebra. If you look up the website bivector.net, it's a website about geometric algebra. And so bivectors are something that work out in that context commonly. I hope from my work to broaden the interest in bivectors beyond just the geometric algebra context. My work can still be useful for that, but I hope that people far beyond that will say, we don't need to replace all of physics, all the mathematics we use in physics. We can just replace this one area, replace the cross products and right-hand rules with bivectors. So that's some background where other people talk about this. Now, beyond all these pedagogical things, the other thing I want to comment on is just that even for experts, people who've been studying physics for years, like me, thinking about these concepts in bivector language turns out to give you new insights and new perspectives on what you're seeing. So just for example, if I want to think about how do I understand angular momentum in relativity, where you've got four-dimensional space-time instead of three-dimensional space? I can't use right-hand rules anymore because it's 4 dimensions. Well, a bivector description turns out to be a very good way of thinking about angular momentum in that language. And roughly speaking, you take the 3x3 matrix that I talked about and make it a 4x4 matrix, and suddenly you've got your angular momentum and relativity explained. The bivector tiles can even tell you things about how rotations work and things. You could ask, how does rotational physics work if we live in a universe with extra dimensions, like string theory talks about, or just for fun to imagine it? And again, traditional right-hand rule stuff will never get you there, but the bivectors can take you there. On the electromagnetism side, it turns out there are cool things that come from thinking about magnetism as a bivector. Just for example, it turns out that there's a very accurate way of thinking about this that says that an electric field is just a magnetic field bivector tile that has been tilted in the time direction. So it's a tile that points in the time direction and in the space direction, and that looks to us like electricity, like an electric field. That's a perspective I'd never imagined before that I've learned after starting this project. It's pretty cool. And if you want to talk about how magnetic effects work in extra dimensions, only bivectors can get you there. Theoretical physicists who talk about extra dimensions have talked about magnetism using the language of differential forms, and that works too, but it's less easy to visualize, and bivectors are very closely related to that language anyway. So this is a good bridge to the way that theorists who work in those areas work on them. All this is to say that experts can get something out of this too. All right, so summing up all of this, I'd say that teaching physics with bivectors can reduce students' confusion and can give them new insight into familiar physics. And it's true. And I want to say a word about what I mean by that. Uh, there are pros and cons. I'm upfront about this. There are pros and cons about this bivector description of physics. It turns out that there are trade-offs. The advantage of the traditional version, even though you have the complicated right-hand rule stuff to deal with, the advantage is that everything is a vector. Anything with directionality is a vector. You only have to worry about those little arrows and nothing else. You are asking more of students, asking more of people to learn both vectors for forces and velocities and things, and bivectors for magnetism and rotations. It's two different types of objects. Maybe the bivectors are easier to work with, but it's still a new thing you have to learn to work with. Whereas the vectors, the traditional form, it trades it off different ways. Both have their challenges. I don't think either one is necessarily easier or harder than the other for a new student. But if you have to choose between the two, shouldn't we teach them the one that's more fundamental? The one that works in mirrors, the one that works in two-dimensional examples, the one that works in higher dimensions, the one that gives new insights into things. That's my claim, is that the bivector story is a little cleaner that way. And I will say, obviously, in teaching these things, a student in my class will still have to talk to people who've learned in other classes. Every textbook they read today is written in the traditional vector form for rotations and magnetism. Everyone else they talk to is, we need to teach them the right-hand rules. We need to teach them some of those things. And I still think, from my experience in my classroom, that students find going to the tile first and then a right-hand rule based on the tile, they find that, my experience has been, they have found that to be an easier time of figuring out right-hand rules than the traditional cross-product stories. I tell them, draw the parallelogram, the two arrows, tip to tail, close the parallelogram, and then use your right hand to figure out where the vector goes. And they all seem to nod and smile at that. It's a very direct way of doing this, and I think it has some real value to it. So even if you're not leaping all in on bivectors, even if it's generations away that people might start thinking about physics in these terms mostly, I think it's still worth teaching this to our students, and it's still worth learning it for the experts out there. That's my story, and there's lots more I could tell you, but I should stop somewhere. If you have questions, I love talking about this stuff, so let me know. But I hope you've learned a little bit about what's exciting me these days.